Hey guys, in this video, we're going to talk about two-way ANOVA, also the Tukey-Kramer procedure. And two-way ANOVA is also called a two-factor ANOVA. So it's a little bit more complicated compared to one-factor ANOVA. So we're going to get to the details in a second. So learning objectives, so we're going to learn how to analyze the ANOVA output from two-factor ANOVA, and then conduct and interpret a Tukey-Kramer analysis of test procedure after we determine that some factors are different. We're going to nail down which factors are different. So basically, we have two types of factors. One of them is called row factors. Secondly, it's a column factor. Okay, so we're going to get to details in a second. So examine the based on the two-way ANOVA outputs, Excel outputs. So examine the effect of two factors of interest. So we call those row factor and column factor. On a dependent variable. So for example, let's say you want to find out the relationship between the percent carbonation and line speed on soft drink bottling process. Right? So we have two factors here, percent carbonation, and the other one is line speed. Okay. And also we try to understand the interaction between those two factors on different levels of those two factors. So does the effect on the particular carbonation level yields different result when the line speed changes, right? So that's kind of the interaction effect we're looking at from different areas. So now the given assumption here for two-factor ANOVA, population normally distributed, population have equal variance, right? And also meaning sigma 1 square equals sigma 2 square equals sigma 3 square, etc. Right? And then independent random samples are selected, meaning our samples are simple random sample. Samples are simple random sample. So we guarantee the result is unbiased and objective. So some useful terms here we need to understand. So two factors, factor A is called a row factor. That's another factor called factor B, that's a column factor. So I'll represent number of levels on factor A, which is on the row factor. And then C represents number of levels of factor B, which is column factor. M prime is the number of replications for each cell, right? For each subcategory, you can also look at it as a subcategory. So N represents total number of observations in all cells, meaning the entire sample size. And that's a formula for that. So you multiply number of rows times number of columns times number of replications, right? And then xijk, subscript ijk, meaning value of the k observation of level I and level I of factor A and level j of a factor B. Okay. Level j of factor B. Okay. So let me use a concrete example to show you what this is, right? So in this case, this is one of the examples here about filling machines. So we have three types of machines. It means we have three columns, so C equals 3 here, right? And then in this case, we have 5 different boxes, box 1, 2, 3, 4, 5. So I equal to 5, we have 5 rows. Right? And then M prime, that's the number of applications. So if you look at it, under each subcategory, like machine 1, box 1, we have 2 observations, or is 2, right? Also, similarly, if you pick another group, right, let's say machine 3, box 2, you have 2 observations, so number of applications will be 2. If you look at the sample size, will be, you see, number of rows, 5 rows times number of columns, 3 columns, right, and times number of applications. So look at it, it's 15 times 2, so it's 30 total data here. So if you count it, so 2, 4, 6, 8, 10, right? 10 times 3, that's 30. So that's how they come up with this. So if you look at this, let's say one of the given data here, and if you look at 23, that will be a machine 2, right? And then box number 2 and second replication, right? So that's kind of like index. So xijk basically is giving us index of each data values. Oh, that's how you look at all those different kind of terms here and related to actual context. All right, and we're going to see a ANOVA summary table. You can also call ANOVA outputs. This is a typical ANOVA output. So in this table, we have a source of variations. We have row factors has variations, column factors has variations, interaction has variations. Also, we have errors, right, which is within all those entire sample. Okay, and degree of freedom for row, it will be number of rows minus 1, right? So in that example, we have 5 rows, 5 minus 1 before. Okay, and sum the square from the row factor SSA, sum the square from column factor SSB, and sum the square from the interaction factor, right, SSAB. Okay. So all of those, and then the degree of freedom for column will be number of columns. So in that example, in the filling machine example, will be 3 minus 1, that will be 2. Interaction is R minus 1 times C minus 1. So sum the square of interaction. Right? So and then we're going to get mean of square by dividing sum of square by the degree of freedom for each corresponding row, column, and then interaction. And then also we're going to get mean of square error by dividing sum of the square error by the degree of freedom. Degree of freedom for error will be R times C times M prime minus 1. Okay. So in that example, that will be 5 rows, 3 columns, and then number of replication will be 2 minus 1, so it will be 15 times 1, degree of freedom will be 15. Okay, so mean of square error equals sum of the square error dividing by the degree of freedom. And based on that, we're going to calculate the F statistics, F values. So test statistics, F values. We do MSA divided by MSE. So mean of square for row factor by mean of square for error, or mean of square within. Okay. And we find F values for the row factor. For the column factor, we do mean of square for the column factor dividing mean of square error. And also for the interaction factor, mean of square interaction over mean of square error. So we get all those F values, and then each F value will yield P values. And if the P value less than alpha, then we reject HO. So we're going to explain the 3 hypothesis testing here in the two-factor ANOVA in a second. Okay. So this is one of the. Okay, one second. Let me find that PowerPoint note. This is the one. Okay, so two-factor ANOVA, the F-test statistics. So first one, we're testing for the factor A, right? That's a row factor. For the row factor, we're assuming, if you look at it, in this case, row factor, we have 5 rows. We're assuming those 5 machines produce the same outcome, right? So HO is all the population means are the same. H1 is not all the means are the same. Okay, or at least one of them are different. Right? If you want to put it another way, at least one is different. Okay. So again, we're using F values, F statistics compared with the critical F values. That's when we do it, or F values yield P value, and we compare P value with alpha, right? And the P value is less than alpha, we reject HO. Reject first scenario, reject HO. Is the second scenario, the P value greater than alpha, then fail to reject HO. Okay, so basically two outcomes. And also we do the F test for the factor B, which is column factor. So similarly, we're assuming those columns, machine 1, machine 2, machine 3 yield same outputs, right? So so meaning HO null hypothesis is all the population mean are the same. Alternate hypothesis is not all the means are the same, right? So at least one of them are different. So no big difference from the one-way ANOVA. And also we will test for the interaction. F test for the interaction effect, meaning does those two factors have interaction between each other. So HO interaction of the column factor and the row factor is 0, meaning this, another way of saying this, will be no interaction. And then H1, its interaction of the A and B is not 0, so that means there is interaction. Yes. And still doing the F test, so we do mean of square between the interaction over mean of square error, and that's a test statistics F values. Compare that with the critical values as a one method, or F value yields the P value. So compare the P value with alpha. So we yield two different results: either reject HO or fail to reject HO. And that's basically three different F tests in terms of testing three different column factor, row factor interaction effect. So again, let's go back to this example about two-factor ANOVA with replications here. So as a production manager, you want to see if three filling machines have different mean or average filling times when used with 5 types of boxes at a 0.05 level. Is that a difference in machines, in boxes? Is that an interaction? So we're testing machines are the row column factor, boxes are the row factor, and also the interaction. So I'm going to use one of the example and show you how to get the ANOVA outputs and also analyze the ANOVA outputs in a second. But let's take a look at this ANOVA outputs for this example here. So for source of variation for row factor, for all those 5 different boxes, degree of freedom is 4, sum of square error is 7.4714. So mean of square for the row factors will be sum of square SSA by degree of freedom. So in this case, it's 1.8678. Okay, so get that one. And for the column factor, degree of freedom, we have 3 columns, 3 minus 1 is 2. And the sum square is 106.298. So dividing 106.298, sum the square for the column factor by degree of freedom, we end up with a 53.149. And now the interaction will be number of rows R minus 1 times C minus 1. So 5 rows, 5 minus 1 is 4. And C is the number of columns, 3 columns, 3 minus 1 is 2. So 4 times 2 is 8. So degree of freedom for the interaction is 8. and the sum of the square from the interaction is 9.7032, and I find the quotient is 1.2129. All right. And the last thing is find out the mean of square error. So we do the degree of freedom. So R times C times n prime minus 1. So as I mentioned earlier, R is 5, C is 3, n prime minus 1, that's 1. So degree of freedom is 15. And sum of the square within sum of the square error is 7.5994. And you do sum of the square of error dividing by degree of freedom, right? We end up with 0.5066. Then for each f values, right? So dividing this 1.86 mean of square. So f values here is mean of square for row factor by mean of square error. So end up with this number. So mean of square of a column B over mean of square error, we end up with 104.906. So dividing this by that, right? And also interaction, dividing the mean of square of interaction by mean of square error, we end up with a 2.3941. And each one of these will yield the p-values. Right. So in this case, for the row factor, since p-value is less than alpha, that means we reject HO. That tells us at least one box yields different results, right? Yields different result. Meaning not all population mean are the same, different result. So that's what we get from the hypothesis testing. And look at the column. So the p-value is 1.52 times 10 to negative 9 power. It's definitely less than alpha. That tells us reject HO. Okay, meaning at least one box yield different result, right? At least one machine, one type of machine yields different result. And for in terms of interaction, because the number is greater than alpha, that means we fail to reject HO. For the interaction effect, that tells us it should be there is no interaction, right? No interaction between the column factor and the row factor. No interaction effect between the boxes used and the machines used. Okay. So we just basically run through those three hypothesis testing, and also since you see we know different boxes yield different results, right? At least one box yield different results, so we can do Tukey Kramer procedures on a row factor, right? On the factor A, which is row factor. So first of all, we will calculate a critical range. So look up the QU, right? Q values from the Q table, and then here the degree of freedom in that previous example is 5, right? And also number of rows is 5, and then 5 times 3 times 2 minus 1, so it's 15. And alpha equal 0.05, then we'll be able to look up the Q values from the Q table, and multiply by square root of mean of square within, or mean of square error, same thing as mean of square error, dividing by number of columns. So in this case, we have 3 columns, number of replications 2. And this number comes from the mean of square within, it's 7.5994, right? 7.5994. And based on all those numbers, and we throw into the formula, we find out the critical range, and then we compare the absolute difference between the means, right? And then compare that with the critical range and determine whether there's a significant difference between those two different rows, right? Among different rows. So again, compute by formulas only. So I'm using this formula to find out the critical range. Mean of square within, mean of square error come from ANOVA outputs. Okay, so once we run the analysis, it will come up. Yes. And also Q table, we are using that. You will find the Q table from our level course. So R here is the number of levels factor A, which is the row factor. We are doing the Tukey Kramer procedure on the row factors, and then RC times n prime minus 1. So use those two to find out located the Q values from the Q table. And C is number of levels of factor B. So in that previous examples, SC is equal to 3. M prime is the number of repetitions. So I will just try to explain all of these terms here. And also, because of the ANOVA outputs here, so there's at least one machine yields different results, right? So that's a difference between the column factor as well. So we can also run the Tukey Kramer procedures on a column factor, factor B, which is column factor. So one more time, we need to look up the Q values from the Q table. C here is 3, right? And I is 5, C is 3, M prime minus 1, that's 2 minus 1, so it's going to be 15. So Fi is 0.05, right? As usual. And based on the three numbers, we can look up the Q values from the Q table. So one more time, maybe let me just go over this. So let me go to the Q table. Go to our variable course, click on the tables, and open the Q table. Okay, let's see. And I'm gonna see right here, degree of freedom from the numerator is gonna be 3 columns. Right? Okay, that's right, 3 and then 15, alpha 0.05. 3 and 15, so the Q value here is 3.67. Okay, so let's go back here. So this Q value here 3.67. And mean of square within, we find it from the ANOVA output 7.5994. 7.5994. Yeah. Okay. And also R here, number of rows. In this case, will be 5 rows. N prime is 2. I'm just throwing all the numbers into the formula, and now we're going to get a critical range, and we compare each pair of the absolute difference with the critical range, and we decide on the whether they are different or not. Okay, so C is the number of columns, level of columns. Okay, column factor. RC times n prime minus 1, those two are needed to look up the Q values to you. I is the number of levels of factors, row factors, n prime is number of applications as well. So that so for this particular topic, in this section we just talk about the two-factor ANOVA, right? We examine effects of the multiple factors, row factor, column factor, interactions between the factors, between row factor and a column factor, row and a column, row factor, column factor, and an interaction effect. perform 3 different hypothesis testing on each factor, and also if there's a significant difference, right? At least one of them are different, we're going to perform 2 Kramer procedures for sometimes for row factor, sometimes for column factor, sometimes for both. Depends on different scenarios. The formula is listed in our PowerPoint. Okay. So that's basically what we covered so far. So now, next thing I want to show you a concrete example. Okay, I'm going to use a, yeah, so this is one of the examples here. I'm going to go through the entire process step by step in Excel. So this machine, right, we have two, this example have 2 type of machines, right? We have 2 type of rooms, right? One of them is called Jetta. The other brand is called Turk. So I have 2 different type of rooms. And we have 4 different type of suppliers. Okay. And we try to measure the strength of the fabric or textile they produce, right? Strength. So here the number represents the strength of the textile. Okay. Now, first of all, so we have 2 different factors. Row factor here is different type of rooms. We have 2 different levels. Okay. And a column factor represents different suppliers. So I have 4 different suppliers, 4 different levels, column factor. And we try to figure out whether or not there's interaction between the supplier and also the type of machine they are using. Okay. So first of all, let's calculate the sample mean, right, from each supplier. So you can just do an average. Okay, open parentheses, highlight those 10 numbers. So in this case, number of repetitions would be 5, right? Okay, and each column has 10 numbers because I have 2 different row machines. I get that. First one is 19.0. Get the rest of them. Okay, and that's the overall. So that's overall difference, right? From the yes. So basically, it's for supplier 1, supplier 2. Okay. And now next thing I want to show you the outputs from the ANOVA. So you highlight the entire table. Okay. And then you're gonna go to data. Okay. And then you're gonna see data analysis. Go to data analysis, and you're gonna pick the one with say ANOVA column 2 factor with replication. So we do have a replication here. Under each machine for each supplier, there are 5 replications. Yes, so we're gonna do ANOVA 2 factor with the replication. Click on OK. Now input range, you see I highlight the entire table already, so that's good, including titles, right? Titles needed. And then number of rows per sample will be meaning number of replications. In this case, will be replication equal to 5, and alpha is equal to 0.05. And then output range, we're going to pick output range here, right here, D15. Now once you select, make sure all the numbers are proper in all those selections. Click on OK. Then ANOVA output will pop up, right? It's one thing you're going to see here. So we have a GDA, different suppliers. So first of all, let me just highlight the entire. Let me format it a little bit. So I'm gonna center everything, bold it, and then I'm gonna put this in a table, all borders. I'm also gonna put this in all borders. Yeah. And as well as this. Okay, all borders. And now let me just highlight something. So for different suppliers, I'm just gonna put in the different, I guess, different colors to separate them. So I have 4 different suppliers. Each one of them has an average, right? Let's take a look at that for a second. Okay, I'm gonna Okay, I'm just highlight this. We're going to need that in a second. I'll also highlight the average for the and the Turk for different suppliers. Okay. And if you just look at the average here, look at the overall speaking, right? For under the Turk, using the Turk loom machine, you know, the textile strength is better. You see, the number is bigger, meaning textile strength is better. So that's one thing we observe. And I'm gonna show you later. I'm gonna graph this, and then you're gonna see the difference from the graph. But now, first of all, let's look at this ANOVA outputs, and then let's perform all three hypothesis testing, and let's understand what all those different factors first of all. Okay, putting all borders. So let's look at first of all for sample, which is row factors, right? Same thing as same row factors. For the row factors, sum of the square for row factors 6.97225 degree of freedom. Because we only have two rows, right? Two levels on the row. So 2 minus 1 is 1. So degree of freedom is 1. And the quotient between the sum of the square from the row factor by the degree of freedom, that becomes 6.97225. And then the corresponding F values, we divide this mean of square from row factor by the mean of square within. Within same thing as same error. Okay. Then mean of square from row factor by mean of square within, we get this. So it becomes 0.809573573. And also the column factor, sum of the square from the column factor is 134.34875. And we feel like this decimal is too much, we can reduce it, right? We can go to home and try to reduce down to less decimal place. That's okay. Same thing here. We can reduce down to a couple decimal place for a simplification reason, but we can expand it as well, right? Yep. So, and degree of freedom, because we have 4 different suppliers. So number of columns is 4. 4 minus 1 is 3. So when you're dividing 134.35 by 3, you get 44.78. Interaction, sum of the square interaction is 0.29. Degree of freedom, so it's R minus 1 times C minus 1. So will be 1 times 3, right? Will be this. Basically, degree of freedom for interaction will be the product of the degree of freedom for rows times degree of freedom of column. 1 times 3 gives us 3. And degree of freedom error, so it's R times C times M prime. So here R is number of rows, 2 rows, times number of columns, 4 columns, right? Times M prime, which 5 replications minus 1. That turned out to be 32. So that's why the degree of freedom for within, right, it's going to be 32. And then we're dividing 275.59 by 32, we end up with 8.61. Then we divide each one of the mean of square from the row factor by mean of square within, we get F values. Mean of square from column factor by mean of square within, we get the F value for column. Mean of square interaction dividing by mean of square within, we get a F